Welcome to this College Algebra tutor training video. This training video is all about rational functions. We'll talk about graphs, intercepts, and asymptotes. First off, a rational function is a ratio of two polynomial functions. So, polynomials of any degree, one in the numerator and one in the denominator. It'll look something like this. So, where a and b are leading coefficients, and n is the degree of the top, and d is the degree of the bottom polynomial. So fractions, pretty much fraction functions of dividing any polynomials. Here's some idea of their shapes. There are a lot of different shapes that rational functions can take. So there's usually some slightly curved lines and some asymptotes. That's what those dashed lines represent there. It just depends on the type of rational function is. We'll talk more about asymptotes in a minute, but first let's talk about intercepts. You remember those from way back a couple weeks ago when you talked about them in your other training. But intercepts, it's the same process no matter where the function is. You're just plugging in zeros. So if we're going to find, let's say, the y-intercept, let's go ahead and do that. We're going to plug in 0 for x. So we're finding f of 0. Plug that in. I love plugging in 0. 2 times 0 is 0, so you get negative 6. 0 plus 12 is 12. That simplifies to be negative 1/2 or negative 0.5. So the y-intercept is going to be the point 0, negative 1/2. Okay. Let's find the x-intercept. Do that over here. We're going to plug in 0 for y, or f of x, and solve for x. Nice thing about this is you really end up looking at the numerator. So, for example, I can just multiply both sides by the denominator. X plus 12 times 0 is 0. Or you can just look at the numerator. Add 6 to both sides, divide by 2, x equals 3. So my x-intercept is 3, 0. Let's look at that on the graph. Yep, so 0, negative 1/2 is our y-intercept, and our x-intercept is here at 3, 0. Now sometimes you will come across graphs of rational functions that do not have intercepts. Maybe they have asymptotes on the axis. So you might, when you're solving for intercepts, get undefined or something that doesn't work out. So that's how you know that there's no x or y intercept when that happens. Alright, that's intercepts. You know how to do those. So let's talk about asymptotes. If you look at these graphs, the curve gets closer and closer to the dotted lines. Doesn't actually cross it except in one case. We'll talk about that in a minute. So the idea is that as you go farther out, the curve gets close to that line. A line that a curve approaches as it moves towards infinity. So for example, as x gets bigger and bigger, this function here gets closer and closer to that horizontal asymptote at positive 5. Or if we go look at one of these vertical ones, as y gets closer to infinity, this gets closer to the line x equals negative 2. It's closer and closer to it. Now, asymptotes do not necessarily mean that they don't ever get crossed. So, for example, on this one I'm looking at here, it crosses at y equals 0. Right? It crosses on the x-axis, which actually is an asymptote as you look to the left and to the right. So the idea of the asymptote is it's just a line that the curve gets close to as the numbers get bigger. Let's look at the asymptotes. Like we have horizontal, we have vertical ones. That's what those abbreviations are. Also on this last graph, we have what is called an oblique or a slant asymptote. This one is slanted right there, that it gets close to. Okay. We're going to first talk about vertical asymptotes. So let's look at those for each of these graphs. On the first graph, the vertical asymptote is x equals negative 4. If we look at the function itself, there's something very important here about negative 4. If I plugged in negative 4, I would get a 0 in the denominator, an undefined function. Okay, on the next one, if I plug in positive 4, the vertical asymptote, the same thing happens. On the next one, if I plug in 2 or negative 2, either one would give me a 0 in the denominator, so those would be undefined as well. Same thing happens on the 4th graph and on the 5th graph. So, in summary, vertical asymptotes, you find those by figuring out what would make the denominator 0. Here's our process. Just figure out what makes the denominator 0, solve for x. So in this example, I'm going to take the denominator. It really doesn't matter if the numerator is 0, it just is when the y equals 0. Right? So x squared minus 1x, just looking at the denominator, minus 6 equals 0. I'm going to solve this by factoring, but you could also use the quadratic formula or completing the square. X and x multiplies to be negative 6 would be minus 3 and plus 2 to get the negative 1. Set these equal to 0, 3, and negative 2. Again, let's look at our graph and see if it agrees. Yep, vertical asymptote at negative 2 and positive 3 for this graph. We can find the vertical asymptotes. Okay, let's talk about horizontal slash oblique asymptotes. So on our first graph, the horizontal asymptote, you can't really see it in this small graph, but the horizontal asymptote is y equals 0. On this one, the horizontal asymptote is y equals 5. And we have another y equals 0 they can't really see. Y equals 5. And on this one, there is no horizontal asymptote at all, but this one does have the slant or oblique asymptote, and it's the line y equals x minus 4. So let's look at the ones that have horizontal asymptotes in common. So on the first one and the third graph, they both have the y-axis. Now let's look at the functions. On this one, we have a constant divided by a first degree. So the degree of a constant is always 0, right? On our third one, we have a degree of 1 and a degree of 2. So when we have a degree on top that is smaller, it looks like we get a y equals 0 asymptote. Okay, we'll summarize that in a minute. On the second and fourth graphs, we have degree of 1 over the degree of 1 and a degree of 2 over the degree of 2. On these ones, you have the same degree. Also, what's 5 divided by 1? Right, our leading coefficients is 5. That's going to be helpful in a minute. On our last graph, the degree on top is bigger than the degree on the bottom. That means we didn't have one. We had an oblique asymptote. All right, let's summarize this. So here's our just generic polynomial divided by polynomial or rational function. A and B are the leading coefficients. N is the degree, the biggest exponent on top, and D is the biggest exponent or degree on the bottom. Okay. If the degree on the top is less than the degree on the bottom, y equals 0 is the horizontal asymptote every time. It's always the x-axis. The reason for that is, if you think about it like a limit, maybe if you've taken calculus, it's the idea of when x is getting bigger, right? Asymptotes happen when the numbers get bigger. So if I have, let's say, x plus 1 over x squared is my function, okay? As the numbers get bigger, let's say let's just start with 3 plus 1 over 3 squared, okay? So 0.4. But let's then go to, let's say, x equals 20. I'd have 21 over 400. Smaller number. Then as x gets bigger again, let's say I have 1,000. I'd have 1,001 over 1,000,000. Each time it's getting really, really small, closer and closer to 0. Because the denominator number is getting bigger faster than the top number. And that's why whenever the degree is smaller on the top, it will always be y equals 0, because it's just getting really, really close to being 0. All right, what if they're the same? Right? Same degree, you're going to take those leading coefficients and you're going to make a fraction out of them, just like 5 over 1 in the last slide. That's always the horizontal asymptote. As an example in this one, imagine that they are growing at the same rate. So maybe we have 2x plus 1 over just 1x. If I plug some numbers in, like 3 again, I'd have 7 over 3. And then I'd have, if I did 20 again, I'd 21 over, if I did 10, I'd have 21 over 10. If I did 1,000, I'd have 2,001 over 1,000. I'm getting really, really close to 2. Because the degrees are the same, they're growing about the same rate. And so it's like they're becoming 1, and we're just left with the coefficients. Last option, if n is greater than d, there's no horizontal asymptote. The reason being is similar to the first one. The numerator is growing way faster than the denominator, so it's getting bigger and bigger and bigger. There's not going to be a limit on that one. It'll just approach infinity. So, one more thing, if you have where the degree on top is just one more, like x squared over x, than the bottom, then there is an oblique or a slant asymptote. You find that by using long division. Whatever the line is that comes out, that's your slanted asymptote. Most Math 110 College Algebra classes don't teach that, but if you ever want to find it, that's how you do it. Let's try one example. So we're looking at the degrees. The degree of the top on this rational function is 5, and the degree of the bottom, oh, look, it's also 5. So this is one where they match, so we're going to take those leading coefficients, and that is our asymptote, or 1.5. If we graph that, it would have an asymptote there. All right, that is rational functions, but before you go, enjoy these math jokes. You're welcome.